Dr. Zubayer Ahammed. I work at Variable Energy Cyclotron Center. It's in Kolkata. Actually, Variable Energy Cyclotron Center is one of the Institute of Department of Atomic Energy, Government of India. And we as an institute also participate in CERN experiments. And there are 4 CERN experiments. Yeah, ask something? There are 4 CERN experiments, the CMS, Atlas, Alice, B and Alice. We work for Alice and the fully funded by Government of India. So it is our responsibility to tell what we are doing there to the Indian citizens, and you are the future of India. That's why actually I will say a little bit what we have done. Okay? So all you have heard about the Big Bang. Now, what is Big Bang? Yeah, so the theory says the universe was created by a single explosion. That's the theory. Okay? So, and it happened approximately 13.7 billion years ago. And you can see this, there was a single explosion and the universe expanded and cooled down. But what is the proof? Somebody says and you believe, then this is not science, right? What is the proof? That yes, it happened like this, or it was not created by different way. So there are some argument behind it, and that tells us that yes, that could be the reason. Okay? So the evidences are, as per the scientist says, that universal expansion and Hubble's law, one of the evidence, the background radiation, whatever we measured today, and the radioactive decay, and other stellar formation and quasars. You may not understand all these details, but let us try to understand if we can, and if you understand a little bit of it, I will be happy. So what is this Hubble expansion? There is a Hubble observatory. It observed that if you measure the position of the galaxies, you always measure that they are moving away. And the further they are moving away further. What does that mean? They are going away. That means at some point they are together, right? It is going away. Their time is going away. So definitely they are at some point they are together. So that means their creation was at some particular point. That tells you that yes, they could have been created by a single explosion kind of phenomena, and as we are going further, they are going further away. Otherwise, all will not go further away. Someone must be seated at some point, but other is running away. Like if you want to go outside from this room, some people will be listening, but other will be going out, right? Or someone will go out. But everybody is going out further the moment you are, whenever you detect or try to observe it, that means they were at some point. That tells you one of the evidence that they were created at single point. Now another, background radiation. The theoreticians calculated if this was the case, that the universe was created at a single explosion, so there will be a lot of radiations at that point, and they have measured it, estimated it. They have not measured it, they have estimated it. Now, what happens? So do you know what is background radiation? For example, you switch off all the lights. There won't be any light. Or you want to measure the intensity of this light inside the room. What will you do? From this particular bulb or particular tube, you have to turn off the other tubes, other bulbs. So background radiation is that radiation where no source of radiation is there. So you want to measure the light luminosity from this particular tube, it will turn off other. Then you know what will be there if nothing is there, and you turn it on and measure it, right? So just get it, subtract it, if it is not existed, and get the final one, right? So that theoretical calculation says, and it matches with that radiation estimation. So this also points us to that particular point. This is another evidence. Now the radioactive decay. We say this particular rock, that particular universe is of 100 million years, 200 million years, 1300 million years. How do you know? Can you measure it? I have not lived that many years. How do I know? Right? So there is a process called carbon dating, or that process, the one can measure that the creation of the earth, the rocks, when they were created. And it has been found that, for example, the moon was created first, then earth. So all these measurements, all these calculations, they have points at to the particular formation point of formation of galaxies. So this confirms also another Big Bang, the signature of another Big Bang explosion. Okay, and likewise. So what happens after three Big Bangs, 3 minutes of Big Bangs? That universe grows in size and larger, and from Einstein's theory, everybody you know that much, that E is equal to the energy released is the mass of that object multiplied by the velocity of light square. So you get the amount of energy released, and from there, ultimately, what they do? They form photons, nucleus, neutrons, and all these atoms. Okay? So, Big Bang was created here, and after explosion, you have different kind of forces at that time. So if you go to the time scale, 10 to the minus 43 second to at present now, 15 to 10 to the 9 years. So the evolution of the universe. So at that time, the Big Bang, and then as the system goes, we have we know. So what I said, that this inside atom you have the nucleus, and the nucleus are made up of nucleons, photons, and neutrons. And these photons and neutrons, they are made up of tiny particles called quarks and gluons, and they were then free. So at what time they were free? You see, the quarks and gluons, they are free at a few microseconds after the Big Bang, and that time the energy scale was of the order of TeV to 150 MeV, and now the common energy is 0.5 MeV. So what you have to do, if you want to create a Big Bang and prove that yes, Big Bang took place, and we want to confirm that. So you have to, some theory says, so you have to do experiment, otherwise this won't be signed. Someone says and you just take it, accept it. There must be a logic and argument with physics, with science, but it has to be proven by experiment. Then we accept it, yes, this is the correct, right? And I hope you will also grow like this, that anybody says anything, just don't accept it. Show the logic and prove it by experiments. Okay? So we have to prove the Big Bang. And we cannot do that kind of explosion, otherwise we will be destroyed. Even we can do it by exploding by many hydrogen bombs or any nuclear weapons. Okay? So the option is, okay, why don't we create that kind of situation in the laboratory, if it is possible by any means, and see whether this explains my observation, right? That will be the only option. And that is why we are planning experiments at different places. The experiment at CERN is not the first of its kind. You may have heard. The experiment started in the USA first in E735 experiment. Then there is a collider called relativistic heavy ion collider at, we call it RIC, at Brookhaven National Laboratory, BNL. And you will be happy to know that we participated in this experiment at RIC, Brookhaven National Laboratory. In India, there are a couple of universities, and Variable Energy Cyclotron was the leader of that experiment. This ended in 2012 only. So when CERN started and taking data, in parallel, that experiment was also going. So we had the experiments. Basically, we used that our knowledge to at CERN experiment. Okay. So we create this kind of, try to create this kind of situation in experiment. So what is that experiment at present I am going to tell you about. That experiment is at CERN, European Center for Nuclear Research, and this is basically the 27-kilometer circumference of that. So at CERN, this is basically the Large Hadron Collider, where a collider means it collides. Actually, why do it call it collider? Back to back, that's fine. But there is another way also make collision. That you are seated there, I just hit it. That can also create, right? That also release energy. That is also being done. But in this case, why you are doing collider? Because if you want to make more and more energetic particle, you have the dx by dt v, and then kinetic energy will be half mv square, right? So you have to increase the velocity. If you increase the velocity, you have to travel large distance. So you have to travel long distance. Instead of doing that, why don't you move like this way? And you are basically traversing large path and increasing your velocity, right? And that's why these colliders are made, and the energy of the particles are increased and making the colliding particle more energetic. So these are the basically, I just wanted to show you these 4 positions of these 4 experiments at CERN, at LHC, and why this picture? This picture just to show you that this is about 100 meter down the Earth's surface. So if this is the Earth's surface, at 100 meter down, you have these 4 experiments situated. Okay. So now about this slide, how we make this situation in lab. We can think of 2 scenarios in going little bit towards physics. You can create during that Big Bang, so lot of energy released. So you can estimate the temperature, how much it was created, and particle density was also very high. So if you can create that much temperature in the laboratory, how you can do? You can collide by this 2 particle, okay? Or you compress the particle such a situation that it explodes. Similarly, likewise, you can think of this way. Suppose you have some earthen pot and you put matter inside it, start putting it, at some point, the barrier of the earthen pot will break because it cannot hold further, right? So that is the case basically in case of, we call it high baryonic density, why we create in that case. And the heating on, you understand clearly that if you collide 2 particles, the heating situation will be generated. This high baryonic density we call is basically occurs in neutron star. And see how the collision takes place. So you have 2 particles, and after that the one basically taken input from real experiment. So you have these 2 particle colliding, and due to the collision, lot of particles are produced. And immediately during the experiment, we do online reconstruction of the particle. Reconstruction means you have many detectors, right? How you will know that unless you talk to me, I will not know your name, you will not know me. What you are doing, I do not know unless I ask you. So interaction is needed. So detectors are basically some instrument where particles will interact with the detector material. And during that interaction, it will give its signature. What type? From here up, I ask your name, then you will tell, then I will know you. From where you are, so you will say I am from Bangalore. I will know that also in terms. Similarly, you know that there are 2 types of particles in terms of charge, positively charged or negatively charged particle. Also another type of particle, neutral. That means they don't have positive, they are neutral, right? So their interaction with the detector material will be different, right? So the positively particle will the charged particle and neutral particle will be different. So if their interaction different, then the single instrument cannot detect all the particles. That is why in these experiments we have many kind of detectors. Those who will detect the neutral particles, those who will detect the charged particle, also the physics quantities, as I just talked to you about the momentum, the velocity, right? So actually this is a little bit tricky. the low momentum particles or low velocity particles, they will interact with the detector material different way than the higher momentum particles. Also, that is why for high momentum particle detection you also need different type of technology. Otherwise, what will, you will get some signal but you lose many particles. So the scientist has to decide many of the aspects of these particle productions and design this detector and install it. Now the point is, this detector has to be made, built, and then installed. So you have to know beforehand, if I collide two particles, say two proton or two lead nuclei, how many particles may be created, how they will be spanned over the phase space, what will be the momentum or velocity of those particles, will it be the zero momentum particles or will it be 100 GeV particles. So we have to know beforehand, before designing these detectors, by we call it simulation. So there are some packages, I will not term in that packages, I will term some model, some theory calculations. On the basis of the theory calculations, and also these theory calculations are enriched by the experience of earlier experiments. For example, I said we did experiment at RIC. So we knew that time the energy at RIC is lower than that energy at CERN. So we knew that if we collide these two particles at this energy, this many particles produce. And this was the momentum range of these particles. So we have some pre-hand knowledge. So what will happen, what may happen if energy is larger, what will happen? So that information, that knowledge we incorporate into our calculation, and then on the basis of those calculations and optimization of these parameters, giving some wide range, suppose this calculation goes wrong, so plus minus, so, you said, for example, if I ask you how much is the distance from BITM to railway station or your home, you will say 2.3 kilometer, but actually it can be 2.2 kilometer also, unless it is measured accurately, right? I don't want, during experiment, I don't want to miss that information, because if I miss, it's a huge loss for me. I don't want to redesign, I cannot redesign again. It will take a long time. So we give some span. Within that span, we design our parameters, and these detectors are installed. And during experiment, and this is basically online, so experiment took place, we have a software that what is happening, we can immediately recapture, and we can reconstruct. That means there are several detectors, so the particles will give signal in several detectors. So you know what, how many point you need to draw a straight line? Minimum 3, right? So if 2 you can make it, but 3 will better. So if you have the larger number of points, larger number of the path will be detected. Suppose you want to go to that end of the hall, you can go through this way. You can restrictly go that way, right? So you need points from where you are going. The detector will give those points, and you combine those points, and that point we call it a reconstruction of the particle points. So after that reconstruction, we measure those particles. And so this is basically, I will not go through in detail, this is really the physics in terms that if collision takes place, then what happens? This is the case of before collisions. And then after we have an equilibrium, we call it hadronization, and we freeze out. But since it is written, let me just tell me what is chemical equilibrium. This basically the state where the Big Bang, the signatures of the physics signatures is equivalent to the Big Bang. We call it quark-gluon plasma. Means quarks and gluons are not confined in the nucleons, rather they have come out of the barrier, they are free to move. Okay, and this we call it chemical equilibrium, means no longer new particles are produced, they are just interacting with each other, and they form they form into hadrons, and ultimately freeze out means they goes out of the reaction plane, and these particles in the final state particle we detect in the detector. So now this is the Alice experiment I was just talking about, and there are 18 different technologies. I already explained to you why do we need different technologies, because of the different particle nature, because of the different physics signals, and we need different type of detectors. And also the size is about 16 to 26 meters. That I am not, if you remember, doesn't matter because that's not the point to explain you here. Only thing I want to mention it here, the two detectors here, you see this called written PMD, and here is the muon tracker. The PMD stands for photon multiplicity detector. Okay, and photon is the neutral particle, you know that, right? And so this our detector, the photon multiplicity detector, is to count the number of produced particles in such experiment. And also there was the muon tracker. There was one also, the muon chamber built by Science Institute of Nuclear Physics, and they built one of the stations of this muon chamber. You know what is muons. Muon is the weakly interactive particle, and lot of cosmic muons are passing through you also. They do not interact with matter. So to detect them, you need a special technology. So this detector was one of the station was built by Science Institute of Nuclear Physics, and our photon multiplicity detector. Now I can briefly tell you. I hope you will understand this way. So we know there are two types of particles, as I said, in terms of charged particle and neutral particles. Now in the all the particles are after produced, they are moving all around. So in these detectors, this is gas detector. So what will happen if a neutral particle goes? It will mostly do nothing. But if a charged particle goes, it will ionize, right? And you know, understand what is ionization. It will take out an electron from outer orbit of the gas. Okay, so it will ionize the gas, and then it will create ions and electron, right? So the charged particle will do that, but the neutral particle will not do. So what we have done, we have made it two layers of same detector, a gas built-up detector. In between we have put a lead material. Now the photons, while passing through the detectors, the neutral particle, in the first layer of the detector, it will not give anything. But after that it will face the lead, and if lead is, you know, the atomic number Z is very high. So the photon, what happens, it is converted into positron and electron. Now the photon no longer is a neutral particle. It has converted into electron and positron. So then it will, you have the another layer, and there it will give signal. So what happens? You have charge and neutral. Charge particle will give signal to both the layer of the detector, but photon will give only one layer. And just simple by this logic we use this photon multiplicity detector. Of course there are other technology involved with it. I am not going into detail. Just try to I try to tell you so that you can understand a little bit of it, how it works. And so this is the many large number of these experiments are so big that a single person, a 2-3 person cannot do it. There are many aspects. You have the detectors, you have to run the detector, you have to run the software, and you have to do the physics analysis also. So in the Alice experiments involved 37 countries almost, and 154 institutes, and almost 1,500 scientists and engineers and technicians, and almost 100 from India out of them. So in terms of India, who are the participating institutes? We have the Variable Energy Cyclotron Center, then Institute of Physics Bhubaneswar, the NICER Bhubaneswar, has recently they have joined, and then University of Rajasthan Jaipur, University of Jammu, Punjab University Chandigarh, IIT Mumbai, IIT Indore they joined now, and Guwahati University they have also joined now, and the Bose Institute Kolkata they have also joined now, and Science Institute of Nuclear Physics Kolkata, and Aligarh Muslim University Aligarh, they are the old members. And also ALICE, we are being the we have associate member Bhabha Atomic Research Center Mumbai, and also the Kolkata University, Calcutta University Kolkata. So and then the physics, you don't worry about this, but still we need to measure it. Sir, what are you doing? What is the measurement? So once we do the experiment, we collect lots of data, and then we do the physics analysis and publish it in papers, physics papers. We call it journals. Okay, and once it is, and these journals are they go through the details of your paper. The student is, they ask you a lot of questions. If you reply them correctly, they accept it and they publish it in their journals. And there are different kind of journals. We measure it in terms of impact factor, that which is high impact factor, which is low impact factor, and we publish our physics results in those journals. On this published, then little bit it's that, okay, at some point it is accepted and it's open to the public. And so this is this slide, basically the jets in heavy ion collision. And this is one of the signature of this quark gluon plasma state, or the related to the Big Bang. So what is that signal? Let me explain you. It's very tough for you to understand, but it's still we call it jets as the collimated production of particles. Means particle produced in a small solid angle, okay, and cone. Now, what is it? Suppose this room is full of people, okay, and empty also. So in case of empty, one person want to run, he will run faster, right? And if it is full of people, then what will happen? He cannot run faster. So in collisions, we collide with proton and we collide with nucleus. In proton number of particles produced less, and nucleus is large, the number of particles will be more. Now the high velocity particles, in case of proton collisions, they can move freely because there is no medium formation because it's lighter, right? But in case of gold or any nucleus collision, since we call this, we assume that the state will form or it will be full of matter, so the particle moving in that direction will, in high velocity, will be less. So we compare that, and from that we can conclude that yes, something has, some new matter has created. Otherwise, the number of particles with high velocity wouldn't have been less. So this is related to that, okay? And this is also similarly the what type of this KGP matter which we have discovered is we discussed in this slide. I will skip this one for you. And this is just the photo of our photon multiplicity detector. This is basically the detector after we cover it. Before covering, the detector would look like this. You have almost 200,000 cells, or we call it 200,000 channels. And it was read by ASIC chip, specially designed circuit. It's called MANAS, and it was designed and fabricated by Science Institute of Nuclear Physics. And you would be happy to know that this MANAS chip, it was designed and fabricated in Science Institute of Nuclear Physics, and also not only the SINP group for their muon chamber detector, almost all ALICE detectors, gas detectors, use that chip. So this is how the photo of our technicians, they are building this detector in the laboratory. And also, this is our test setup at CERN. And when you go CERN, before installing the detector, we had to check and test the detector whether it is working properly or not. So this is basically test bench. And this is one of the photo taken during 2009 at the time of installation. And these are our colleagues. And after that, we have collected lot of data, almost 500 million events we have collected. And also this is the, I was talking about this, the detector built by the Science Institute of Nuclear Physics, the ALICE muon spectrometer. And it's also almost 200,000 pads. And this is all the photo of that detector. It's in terms of our technology, we call it cathode pad chamber, and I will not go in details probably. So, and then what we'll do, this our journey in ALICE, the experiment will go on. There and now it's a long shutdown, 2-year shutdown. So all the groups are upgrading their detectors. So that after 2 years, when it will restart again, we can take data. So though this one, this one is not for this shutdown. After this also in 2023 to 24 there will be a shutdown, and during that time we want to install this forward calorimeter. So here, apart from this photon multiplicity detector, we have completed data taking. So we will go to new technology. There we will be measuring the energy of the particle produced, and that is called calorimeter. So and it is some forward direction of the experimental side. So we call it a forward calorimeter. In terms scientific terms, we call it in forward rapidity region. And so and then. So this is basically the photo of the test of the, and as you have not heard that during these experiments, huge data is produced, and we need to have access from all over the corner of the world to this data. So we cannot send it thoroughly. So by the grid computing process called is grid, we access this data, and this and VCC Calcutta has a grid computing facility where we have almost more than 800 million jobs has been completed. So we work for that also. So and what we have done, so in this program we have, you know what is PhD, right? Yeah. So after your you pass your board exam, you will +2, then your graduation and masters, and after that you will join research, and that research, during that research, you, after 4 or 5 years you get the PhD degree. So in our this ALICE collaboration, already we have 30 PhD produced, and also lots of publications. And during that time also, you may remember that if you enter in masters or engineering degree, you can come to VCC or other associated institute for doing your projects also. We train the project students. And also basically the industry, you need not to worry at this moment, who has contributed to different part of our journey. And now Spinoff, you know what is a Spinoff is that during this experimental journey, the research, we have produced something which has societal benefit, which can be of societal benefit. So one of the is the X-ray imaging, muon tomography, Newton imaging, and top PET. What are these? Basically, these are the imaging technology used at different hospitals or medical centers. We are trying to build our own on the basis of the different technology. For example, using technology called RPC based or GEM based, and if we succeed and we have progressed to a great extent, then the things will be very easier, and we don't need to buy it from outside. So this is the basically, and how it happened that when we started building detector, we had to learn something, and then we learned it and we built it, so we became experts. So that expertise we want to use for our societal benefit, and that is what these are the things. So that's all is that participating in heavy ion program since 1991 at CERN to measure subsystems, the subsystems ALICE from India, the PMD and the muon chamber, and significant contribution in ALICE physics so far. And we have a challenging upgrade program, and the industry is our backbone. So that's it from now. Thank you for listening to me. Yes, go ahead.
Like we have different detectors for detecting.
Yeah.
So are they concentric? So are these detectors concentric?
Yeah, I mean they're concentrating one over the other, right? I'll just go back to the back slide if I can, and then it will be easier for me to make it clear. Yes. So this point, this is the center of the collision. Okay. So in that center, that means at that point, these two lead-lead nuclei or proton-proton nuclei are made to collide, and there is a surrounding that point there is a detector called ITS, inner tracking system. Okay, this inner tracking system is basically silicon based, and over that you have 2 meter by 2 meter time projection chamber covering that interaction point, and over that you have then called EM-cal, electromagnetic calorimeter. So most of the detectors, particularly these detectors which determines the collision point, by which call it ITS, inner tracking system, we made the initial tracking and also the vertex position, and also there is detector called V0. So these detectors must be around the collision point, but other detectors not necessary has to be concentric. Okay. For example, the muon detector, the photon multiplicity detector. So what is the advantage, what is the disadvantage? Advantage is that you cannot place all the detectors at every point, otherwise it will obstruct the other detectors. They cannot even do the service when something goes wrong. At the same time, these detectors you cannot, in physics wise, is called, this will actually cover the forward region. So you need to have some detector there also. So that is why you have to get the basic point of this collision. Some detectors has to be considered, like the collision point and all those, the vertex and other, and also the tracking of the detectors, and also have some detectors in the other spaces. Yes, go ahead.
Sir, was there no time before the Big Bang?
What?
Was there no time before the Big Bang?
Of course there was, but we do not know at this moment. Of course there was.
Should we start with the quiz?
Yeah. Yes, you can start. Is there any question? Yes, go ahead, please. Can you give him a mic?
Will India be a part of FCC?
Actually, this is a question. Actually, you know what is FCC? Future Circular Collider. Again, it will be at CERN. So after this activity at LHC is over, people are, the scientists at CERN are planning and thinking about this future collider with higher energy and all other scientific aspects. So the decision to join FCC, at least from my point of view, as a scientist, I would like to join, but the decisions are made from government level, so they have to decide.
India being associate member,
so
might get something useful
might
to
get
contribute.
something,
Useful to contribute
right,
in
yeah.
that.
But
also.
if you are very much interested to know this decision-making answer, on 30th there is program here, and bosses from Indian government will be here to the program. You can raise this question, okay, and also bring some critical question also. Why CERN is at Europe and why not in India? Why can it build like this? Okay.
Sir,
Yeah.
will you ask the questions and I will bring students?
Yeah, sure. There will be now any other questions? Okay. Yeah, go ahead. I'm happy you ask the questions.
You said that when two particles collide, when they explode, they'll give some more particles.
Yeah.
So in this universe also,
Hmm.
there should have been two particles collided, which produces this universe.
Yes.
Is there any estimation about those two particles?
Well, you know the asteroids, right?
Yeah.
They do collide. Yeah, right? So, but you need to know their estimation. Some other experimental observations are there, and the people do that. So, of course, they do in that astrophysical.
Thank you.
That's right.
If there are no more questions, let's start with the quiz.
So, you know, I was asked that, or told basically that there will be a quiz contest, and yeah, and there will be 2 winners from you, and I didn't know how to conduct. So, what I have done, I have just written some questions. Okay, so
Session. Okay.
2 will get prizes, but do not feel disheartened if you do not get. Okay, just interaction and try to answer. Okay. So the first question I will ask, in an atomic nucleus, neutrons and protons are held together by which force? Raise your hands, do not tell the answer. So you 3, okay, the girl student first. What is? Van der Waals forces.
Weak nuclear force.
Okay. Sit down, please. You are in which class? Huh? BSc?
BSc first year. BSc
First year. Wait. Yeah. Who else there? Anybody who read the question?
Come on, try. Ah, yes. Centrifugal.
Electrostatic forces.
Okay. Yeah, you go ahead.
Sir, please give the
Yeah,
three
so now you give the answer. Yes, that's correct answer.
Strong nuclear force is the correct answer.
Okay.
So put on your thinking caps.
Another question on force again. What is the weakest force in the nature? Very fast.
Gravitational force.
Okay. Anybody else know the answer?
No, that's the same.
Same answer. Okay, then it should be correct. Right. I just wanted to test it. Okay.
Should we call them?
No, I'll just give, I remember him.
Or they can be kept standing?
I will not take much more time. Shall I say that? One more question. It should go to the girls students, don't mind boys, okay? Light year is a unit of? Light year is a unit of?
Distance.
Time?
Time.
Yeah.
Time.
Length, okay. Okay, okay, so yes, she has already replied. She has already replied, that girl. What is your name? Yeah. Mahira, okay. So I give one prize to Mahira and one prize to this. And so thanks to him because he's BS student. No, he gave first. She gave first. Okay.
You can please come
Yeah,
forward.
so
both of
Mahira
you.
and two. And he also can come, but please don't get decided. They are class 9 student, right? Okay.